Okay, what we're going to be investigating are limits as x approaches infinity and as x approaches negative infinity. So we're going to be looking at end behaviors and seeing how this corresponds to limits and asymptotes. We did a tiny bit of this back in the very first unit, but now we're going to use it when we're going to try and put all the sketch of curves together. So the first two that are here, these are kind of building block limits that we're going to need to use moving forward. Here, this is the limit as x approaches infinity of 1 over x. And you can consider this a couple of different ways. If you remember what the 1 over x graph looks like, I'll just sketch it real quick. Okay, it looks something like that with the asymptote here, asymptote there, and as x approaches infinity, it's on this part of the function, and it is going to start tending towards 0, but it's above the asymptote, so that's 0 with the little superscript there being plus. Now, another way of thinking about this is, as x approaches infinity, the denominator is going to become a really big positive number, and the numerator just stays at a 1, which means that what you guys know about fractions is if the denominator keeps getting bigger and bigger, the fraction is telling you the number is actually shrinking and shrinking. So this is tending towards 0, and the fact that it's tending on the positive side of 0 is because the number that we're creating here is always guaranteed to be positive. The numerator is a positive number, and the denominator, as x approaches infinity, this is always going to be a positive number. So that means as this thing shrinks, it doesn't change sign at all, it just keeps getting smaller and smaller, but staying positive. You could use the same kind of logic over here, that as x approaches negative infinity, then the numerator is going to stay at a 1, the denominator is going to become a really large negative number. What that means that the fraction is telling us our number is actually shrinking towards 0, but the fact that I've got a negative number down here and a positive number up here is going to say that we actually are using a negative number as we're actually approaching 0. And if we were to take, let's say, the limit as x approaches infinity of just a polynomial function that doesn't have this kind of relationship between numerator and denominator, then as x approaches infinity, all the terms that are just x's, those are going to grow without bound, and this is not going to have a limit. It's going to go towards infinity. That's there. And you could also think of about this in terms of like your advanced functions lens, where as x approaches infinity, this is saying what's happening towards the right end of the graph. I know that this is an odd degree function with a positive leading coefficient, so it should extend from quadrant 3 to quadrant 1, and this is asking what happens towards the right end of the graph. It's in quadrant 1, so it should be going towards positive infinity. Okay, for this one here, limit as x approaches infinity of 2 over x minus 7, we're going to use a little technique here where we find the highest degreed term in the numerator and the denominator. In this case, it's x to the 1. And what I'm going to do is multiply both the numerator and the denominator by the reciprocal of that highest degreed term. So in this case, 1 over x to the 1. Now, you'll see why in a second. If I distribute the 1 over x into both the numerator and the denominator, then what ends up happening is my numerator is 2 over x, and my denominator has this now 7 over x term, but the x over 1 over x just becomes a 1. And now I can start implementing some of my limit properties, where I could just look at these individually. The limit as x approaches infinity of this is going to look exactly like what we did up here, which means as x approaches infinity, the denominator here is going to start growing without bound, so this is going to start shrinking down to a positive number, but it's going to be approaching 0. This is going to start shrinking down to a positive number that's approaching 0, which essentially means these are both going to 0. So what I should get is these going to 0, this 1 is not being affected because it has nothing to do with the x, so I've got my limit being evaluated at 0. Over here, similar kind of idea. The highest degreed term here is x squared, so I'm going to multiply the numerator and the denominator by 1 over x squared. So what that means then is when I distribute it in, all of my terms are going to get affected, and all of the terms that are reciprocals, so constant on top, and then in the denominator some sort of variable part, all of these, they're going to behave just like either one of these. which means this is going to start tending towards 0, this is going to go to 0, this is going to go to 0, and then the constants are all that's left. So that means that this limit can be evaluated at -3. Now, hopefully you've kind of know some stuff from advanced functions about horizontal asymptotes, because what we've now actually shown is that we've got some horizontal asymptotes for these functions if we were to actually try and sketch these things out. So it says in terms of limits, this line y equals L, that's our horizontal asymptote, is going to be the horizontal asymptote of f if either the limit as x approaches infinity of our function approaches some number that we're going to call L, or as we approach negative infinity, the limit of f of x is L as well. So what this means is that for what we did here in this example, we have a horizontal asymptote at y equals -3. And for this example, we have a horizontal asymptote at y equals 0. Now you may already have kind of like your rule of thumb stuff that you did from advanced functions to already see that, but this is going to become really useful right now, but it'll also be more useful when things get a little bit more complicated, because here I only check towards positive infinity. If I were to check towards negative infinity, this is still going to be true, but that won't stay to be like a true statement for every single function. These rational ones, they're okay, but as soon as we get into some more complicated ones, then it's possible to have multiple horizontal asymptotes, and we'll see that later on in the course. Okay. Now, what hopefully you also remember from advanced functions is that when you're dealing with horizontal asymptotes, all we are looking at are behaviors at the ends of the graph. In the middle, quote unquote, of the graph, it's possible to cross it, because these are not like true barriers like vertical asymptotes are. So we're only really interested towards negative and positive infinity, what's going on, and our graphs are tending towards these lines. But in the middle of the graph, you know, they can do whatever they want. Okay, and the key thing from this is to remember those two first examples. These are kind of our building blocks. Because these ones go to 0, they kind of set up everything else. So let's do a couple really quick examples of this so you can see a little bit more of this. So here it says determine if the following functions have horizontal asymptotes or not. If they do, find them. So let's say for this function here, the highest degree term is x to the 1. So if I want the limit as x approaches infinity of the function, I can multiply numerator and denominator by 1 over x, so the reciprocal of the highest degree term, and then distribute that in. Anything that is a reciprocal now, it's going to tend towards 0, so this is just going to be a 0 over 2, which is 0, so horizontal asymptote of y equals 0. For this one, highest degree term is x squared, so if I do the same type of thing and I want the limit as x approaches infinity of it, then I can multiply numerator and denominator by 1 over x squared. Distribute it in. All the reciprocal parts, they're going to tend towards 0, so this is just going to have the 3 and the 6 left over. So we've got a horizontal asymptote then going towards y equals 1 over 2. And the last example that's here we've got the highest degree term being x cubed. So if I want the limit as x approaches infinity to test its end behavior, then I can multiply everything by 1 over x cubed. And it has to be everything, numerator and denominator. Otherwise you're changing the proportions. So if I do that and I distribute it in, here I'm going to run into a problem, because my reciprocal parts that I have here, the reciprocal terms, they're going to tend towards 0, but that's going to leave me with an 8 in the numerator and a 0 in the denominator. I'm dividing by 0, which means the limit doesn't exist. This thing's shooting up towards infinity. So no asymptote that's there. And this hopefully corresponds with what you guys already know about horizontal asymptotes from advanced functions, that says if you had a rational function in this form, so I've got kind of standard form decreasing in terms of degree of the numerator and decreasing in terms of degree of the denominator. If we look at the relationship between degree of numerator and degree of denominator, then if the degree of the numerator is smaller than the degree of the denominator, we always have a horizontal asymptote at y equals 0. If they have exactly the same degree, then we take the ratio of the leading coefficients, a1 over a2, and that's going to be where our asymptote is. Or if the numerator has higher degree than the denominator, then there's not going to be any horizontal asymptote like we did in the last example. There may be an oblique asymptote, but we will investigate that in the very next video.